All right, hello people, biology people. Let's get into our discussion on proteins, but more specifically, our discussion on enzymes. So up to this point, we've covered chapter 2, all the chemistry stuff. We've got into the chapter 3, all the aspects of protein structure, primary, secondary, tertiary, quaternary. We know the bad things that can happen with protein denaturation. So after 3, obviously we should be progressing into chapter 4. However, I don't understand why the book author Freeman has done this. He puts enzymes, which are a major category of proteins, he puts them all the way in chapter 8. So I'm not going to progress from 3 to 4. I'm going to go from 3. I'm going to hop over to chapter 8, cover the content of enzymes with chapter 3, and I think it's going to be a more cohesive unit of proteins, right? So enzymes are proteins. Everything you know about proteins applies to enzymes. Enzymes are made by the process of dehydration synthesis. Little amino acids combine together through the process of dehydration synthesis. We have the primary structure, the secondary, the tertiary. So all of those things that apply to a generic protein, a muscle, a connective tissue, hemoglobin, enzymes, they're all the same. Enzymes are a category of proteins, but they are very special, very unique in what they do. I couldn't find a better representation for enzymes than these little minion characters. I think they epitomize what enzymes do. They're always active, they're getting into drama, they're causing chaos, and that is what enzymes do. There's a bunch of different types of enzymes, but they kind of fall within 2 big categories. And we're going to talk about the hydrolytic enzymes and then the dehydrative synthesis enzymes. So we'll look at all the idea of enzymes and then collectively the 2 types here. So we start by discussing chapter 8, enzymes as catalytic proteins. They're catalysts. So they catalyze reactions. And that's a very fancy way of chemists saying they speed up chemical reactions. So they don't cause reactions that are not supposed to happen. They just speed up reactions that are already going to happen. The best example I can give you, I think, is an alarm clock. I don't know if you set an alarm clock this morning, but if you did, that alarm clock served as a catalyst. It sped up the waking process. If you didn't set that alarm, you would eventually wake up at some point in the day. Maybe right now you'd still be asleep, but you would wake up at some time. So you're gonna wake up. What the alarm clock does, it just makes you wake up at an earlier hour, an hour that we don't want to wake up maybe, but we have to. So that is what enzymes do. They're these little proteins that cause reactions to happen faster than they normally would if they were not catalyzed. So another important aspect, they don't get used up in the reaction. So they catalyze, but they don't get damaged. They don't get sort of encompassed within the reaction. So they catalyze and then they're done and then they're ready to catalyze again. A good example I can come up with is the pan, like a frying pan. So the frying pan is involved in many reactions. It cooks breakfast, it cooks lunch, maybe it cooks dinner. It cooks all these different types of foods, but the pan itself doesn't get damaged. It doesn't become part of the food that we eat necessarily. So it retains its identity and it serves as the location for the reactions to take place. And that's sort of the idea of not getting used up by the reaction. So that's the what. What do enzymes do? They speed up reactions. Okay, the more technical part, the answer that deals in the realm of physics, how do enzymes speed up reactions? How do they serve as catalysts? Well, we'll go to the second bullet. They will decrease the amount of activation energy required for a reaction to occur. Right, so what does that mean? They decrease the amount of activation energy required for a reaction to occur. In the realm of physics, we learn about the conservation of energy. We can't make energy, we can't destroy energy, all we can do is transform it. Well, same kind of idea here. In order to get something going, you have to sort of put in a little bit of energy first. And that's that energy of activation. And what enzymes do, they minimize, they decrease that input of energy that's necessary. They decrease the amount of activation energy that's required. And kind of not necessarily the easiest concept to explain, but we'll try to make sense of it in a bit. Also, enzymes are going to be part of what we call metabolic pathways. This is a big deal in chapter 9 when we get in there later. We'll talk about metabolic pathways and then the role that the enzymes play. It's a little video of Stewie. It's not linked up to this PowerPoint right now, but I'll see if I can find it and link it into your Blackboard. So it kind of reminds me of this activation energy, this input of energy that's required. Right? So let's kind of deal with this activation energy. So you are maybe this guy right here. I don't know if you've ever been in a flight, you're enjoying the trip, and then you have this kid behind you, right? How many jolts, how many kicks, how many disturbances would it take for you to turn around and say something, right? Some of you are very patient. Some of you are not very patient. Some of you will reach your breaking point sooner than others. But that breaking point would be technically that activation moment. How much kicking and moving was required to get you to that point for you to react, right? And that's what enzymes do. Enzymes would be like this little kid just kicking and kicking and kicking and kicking and kicking until something happens, until that reaction is initiated. So keep that in mind with enzymes. They're little instigators. That's what they do. They cause reactions to happen. The reactions were going to happen, but they cause them to happen in a much more quicker, much sooner type of time frame there. So boring chemistry graph, boring physics graph here. If we look at the black curve, this black curve represents the reaction from reactants to products, a decrease in energy. But before we get to the product, before we transform, before we change, we have to overcome this activation energy. We got to get up to here. Once that energy is achieved, then we can proceed down to the products. So we don't convert reactants into products until we've achieved that activation energy. If you notice the black curve, that little mountain is tall. The red curve, that little mountain is a little bit lower. So it's going to be a little bit faster to get there. And if we get there faster, we're going to get here faster. So the red line represents the amount of activation energy required, which has been reduced with enzymes. So the enzyme has decreased the amount of energy required to convert reactants into products. We get to the same point. We don't arrive anywhere different. We end up with the same product. The red curve just got there a tiny bit sooner. The black curve got there a little bit later. Again, that's what enzymes do. Let me back up. Enzymes speed up reaction. That's what they do. How do they do it? They decrease the amount of activation energy. So again, a little bit of stuff to learn, but it's not, I don't think, super complicated. So I think, spend some time with this, process it, make sense of it, and then, move on to the next slides here. So this is going to make sense to some of you. Some of you is not going to make sense, I know. Some of you had cool toys growing up, yeah? Some of us didn't have the newest toys growing up, but we had big yards and all this place to play behind our house and that kind of stuff. So we would find empty jars, and we didn't have internet, we didn't have PlayStations, that kind of stuff. So what do? You go outside, you play outside. And we would go and catch bugs, catch all these little critters all throughout the yard, right? So this reminds me of kind of an enzymatic process as well. So the jar is going to kind of give us the space the location for then the reactants to be brought in, and the reactants will do their stuff, and then that basically you dump those out, and then the jar is still available for more bugs to come in. So the jar is not damaged by this process. When we had the jar, little bugs are just peaceful, minding their own business, we would shake the jar, right? We shake the jar, shake the jar, shake the jar, shake the jar. So we shake the jar, little bugs get all upset, they get all pissed off, and they start to fight. So in a sense, we would force those interactions to happen. Maybe they were going to fight at some point in their life. What we did, we made them upset, and we made them fight sooner rather than later. A little bit maybe before some of your time, big famous guy, boxing promoter Don King, who I like to consider as a human enzyme, right? I maybe should have put another picture of Dana White, the guy of the MMA, I don't know what you call it now, MMA fighting. He kind of arranges all those fights there, but same kind of concept, right? So Don King, the human enzyme, had all of these fighters, right? And all these fighters, they look quite civil and quite peaceful there. But on Saturday night, man, they're trying to literally punch each other's head off there, right? So how do they do that? Why do they do that? So what kind of activation energy could Don King sort of manipulate here? What could he do or offer for them to decrease their activation energy and start fighting? Right? I don't know if you know a little bit about Don King, but it was all about money, right? So I would ask you, right now, tough economic times, for $20,000. It's a fair amount of change, right? Maybe a new vehicle, something like that, or a big payment on a new vehicle. For $20,000, would you get in a ring, right? Males, females, whoever, tough boxer, female, tough boxer, male, would y'all get in the ring for $20,000 with one of these professional fighters? Yeah, some of you, yeah, I could use 20,000. So some of you like, no, the ambulance ride and then the emergency room, no. So maybe 20,000 is not enough. Maybe 100,000, maybe more, 1,000,000. Right? I think for $1,000,000, you would do a lot of things, right? Your activation energy would like, hey, go slap grandma for $1,000,000. I bet some of you love grandma, but you would go do that, right? So that's the sort of idea. So he sort of got the fights together. These people got all beat up. And Don King was perfectly fine. All the money in his pocket to go kind of set up other fights, to promote these other boxing matches there. So this is the idea of an enzyme. It's always causing stuff, right? I don't know if you've ever started a fight. How many of you had come and instigated to this person? Oh, he talked bad about your mama. Oh, he said this about this. Oh, I wouldn't take that. How many of you have caused some sort of reaction like that? If you have, maybe you acted as a human enzyme as well. So I hope you're getting the idea of our enzymatic sort of behavior, enzymatic sort of activity, what they do. Now we come back into some vocabulary, right? So let me stop this video so it doesn't get too long, and then I will address our enzymatic structure.